me see if I was doing this right. I wasn't sure about the units. I tried to do what we did yesterday.
Let's see. So frequency, and then so
So that's the speed of light one.
yeah, so speed of light divided by frequency to give you wavelength. I just think that number looks funny. Like the setup looks correct, but
Oh, you just got a weird number.
yeah, maybe you punched something in wrong, I'm not sure. Cause yeah, like that looks fine with the setup,
Okay.
but I don't like the number.
Okay. But this, like, did I set it up right and I used the right stuff?
Yeah, and then that would be
Okay. So I'll just
right.
go.
Yeah,
I'll try
just
this
punch
one.
that in again. Oh, yeah, I think I gave out homework, but I'm not sure I brought it with me. I'll probably have to grab it.
No worries.
X plus h into it, yeah. So it'd be 1 over square root of x plus h.
All right, any questions before we get started today? So just looking way ahead on the calendar, so we're ending week 3 today, so next week is week 4, and then week 5 would be midterm week. So just put that on your radar.
Marissa, are you going to talk a little bit about the structure of your exams before the exam?
Yeah, what I usually do is give like an exam review, and I try to do like a representative problem as an example. But in general, they're mainly free response, very few multiple choice.
And are they open note, like
Yeah.
quizzes? Okay.
Yeah, so it'll be open note, open everything, just not open Google, and not open Friends. But yeah, open notes, open book.
And open stranger.
Open stranger. All right, any other questions?
If my book is online, can I still use it?
Yeah. Yeah, so you can bring like a laptop and, you know, you can look at like textbooks online, so that's fine. All right, any other questions? Then if you're in the chat, say hello. All right, let's go into kind of the history of quantum mechanics then. Before we get to Einstein, or brief history. And so it really started back in 1802 with Thomas Young. And he first performed what's called the double slit experiment. And so at this time, they were trying to figure out, well, is light a wave or a particle? So they were debating back and forth, what is it? And so they thought, okay, let's try this double slit experiment. And so by classical theory, and just kind of assuming that it behaves as a particle, what they kind of expect, so you have your light source. So it's going to go, then you're going to have 2 slits for it to pass through. And so they expected, and then behind those slits you have your screen where you look at the pattern that the light creates. And so what they would expect to do is for these light particles to just go straight on through and collect like that. So you would have one cluster there as it passes through one slit, and then a second one for the second slit. Except when he actually performed the experiment, he found that it behaved more like a wave. So light source, double slit, but what was kind of strange is it made an interference pattern. So there were bands of dark regions, but then there were also interference bands of no light. And so there are varying degrees of intensity. Actually, let's just look. Interference. Let's just get a better picture. Oh, as soon as I try to find a picture, I can never find the right picture. There we go. So this is a good kind of interference pattern. So you have strong bands in the middle and then gaps consistently. So this was strange to them. So that's what they would be observing. And so from this, right, they're thinking, well, now it's kind of behaving like a wave. They're still not sure. And so later, so this would actually be repeated later in 1927 with electrons. And they found that electrons exhibit the same behavior. So just like the light, they make the interference pattern. So that was really strange. So same behavior. So kind of jumping back in time. So now we're in the late 1800s, roughly. And so at that time, they were observing black body radiation. And so black body radiation is just, you start applying heat to something, and actually you'll kind of see that next week in lab. So if you apply heat to like a metal, for instance, and you know how it starts glowing like red hot, and then you can heat it up more, and it starts glowing like white and different colors. And so that's black body radiation. And then you have what's called a perfect black body, or ideal black body. And so this is in theory. So then an ideal black body would be completely black, and it'd be absorbing every single spectrum of light, so it would absorb everything. But then whatever it absorbs, it also reflects, so it's going to be reflecting black body radiation. And so again, everything gives off black body radiation. And except there was a problem with this at the time because they were observing this through a classical perspective. And so in their theory with this ideal black body, they found that mathematically, as it would get closer, as the wavelength gets closer to the ultraviolet region, this meant that the black body, the ideal black body, would emit unbounded energy. So something didn't seem quite right there. So unbounded or unlimited energy. So all that's saying, right, your light source gets closer to the UV region, it's absorbing all that light, that means it's also emitting that, but by their classical calculations, that meant the energy went to essentially infinity. That didn't seem quite right. So now, and let's go back in time for a second. So we had mentioned these energy levels. So they had started to observe these spectral lines. And so we had mentioned, and again, hydrogen's the easiest to observe, so that's also what you start with, 1 electron. And so it was in 1913 when they actually observed these hydrogen lines. And with that, they also devised those formulas. And so let's take a look at your book. I'm actually going to go back to page 6 and write the formulas there, because they're related to these formulas. And it's the Rydberg-Balmer equation. So Rydberg was the one that he found this relationship. So he was just, messing with the numbers, looking at the spectral lines for hydrogen. And sorry, let me pull up my notes. And so around this time, they developed the Rydberg-Balmer equation. And so all this is inverse wavelength is equal to, and this is just a constant. So that was just, the constant that he found as he's trying to figure out what might make sense for these different energy levels. So it's 1.097 times 10 to the 7th, and then inverse meters. So that's going to match with our units of inverse wavelength. So we'll get out meters. And this is all times 1 over NF squared minus 1 over n for your initial squared. So you're just taking the difference. So all this is looking at and what he was, devising. And so let's say he was looking at this transition, so 656 nanometers from 3 to 2. And so he must have, just been plugging in those numbers. So your F, so final is going to be 3, initial 2. Actually, it should be negative. Let's see. So let's just practice this and see if I flip the signs. So actually you want to do the other way. Sorry. You just want a positive value is what you're going for. So this is plugging this in now. So going 3 to 2. So 1 over 2 squared minus 1 over 3 squared times our constant. Oops. So plug that in times your constant, 1.097 times 10 to the 7th inverse meters. So then this gives you your inverse wavelength. So then you have to take the inverse of it. And so this would be your wavelength in meters. So 6.56 times 10 to the negative 7th. Or, so multiply that. So I'm just going to do my conversion over here. So times 10 to the negative 7 meters. Convert to nanometers, since they always give it to us in nanometers. So 1 times 10 to the 9th nanometers equals 1 meter. So multiply this by 1 times 10 to the 9th. And so that gives us 656. And so that's that number right there, 656. And so that's basically probably how he, again, came up with this constant, just trying to guess and check and what made sense. And so there we've confirmed 656 nanometers for our Rydberg-Balmer equation. And so this is also just another form of this equation, and I'll give you this in the kind of Rydberg-Balmer form. So we said this was the energy for one energy level, so then of course we can take the difference of them to get the difference in energy, which you can of course also relate back to the wavelength, since we have our energy is also equal to Planck's constant times c over wavelength. So all our formulas relate back. And also E equals Planck's constant times frequency. So all those, right, you can just kind of go round and around. I'll give you C equals frequency times wavelength. And so I'll give you then the alternate form. So that would be your energy difference then is equal to negative 2.18 times 10 to the negative 18 joules times 1 over n f squared minus 1 over n initial squared. And again, it should be a relaxation, but just watch what the question's asking and kind of watch your sign as well. So the only thing that flipping the final and initial would do is just swap your sign. And so if you see kind of one of those problems asking you to calculate either energy or wavelength from the difference in energy levels, you can use either one of these forms of that equation. All right, so now back to where we are in history. So we're here, we're at 1913, so they're kind of dancing around this discrete energy level topic. They haven't quite gotten there. And then, so in 1905, Einstein really came along to explain the photoelectric effect. So they had done this experiment previously, but they didn't have an explanation for it. And again, so back to their classical thinking. So their understanding is if we take, a dim light and we shine it at this metal, so they're going to try to hit this metal with a source of energy, that metal will eventually eject electrons. So they're thinking, okay, we're going to take a light, like a weak light source, we're going to hit it at the metal, and if it doesn't eject initially, if we just keep letting it sit there, it'll just go and go, and eventually it will eject off an electron. So that was their thinking. And so what happened is that wasn't the case. What they actually found is that you had to find what they called the threshold frequency. So they were thinking, we could just shine any light source, but you have to hit it with the minimum frequency. And so what they found, so if you use, for example, like a lower intensity light, such as red, so red we learned has long wavelengths, so less energy. So you could hit it, that metal, with the red light source all day, nothing would ever happen. It would never eject an electron. But then as soon as they went to a blue light source that was at the right energy level, it didn't matter how dim it was, it still caused that electron to be ejected instantly. So now they're confused. And so the other thing was what I was saying with the dim source. So the high frequency light, so having again that blue light that was dim, it caused the electron emission without any lag time. So that didn't really make sense to them. So they were thinking that, if you change the intensity of the light, that would start to change when the electrons would be emitted. So instead, they came up again with that threshold frequency. And so then that caused Einstein to come up with kind of quantum theory and the photoelectric effect. And so he proposed then that light was not just discrete, but rather delivered in little quanta or photons, so little packets of light. So it's like these little packets of light had a certain amount of energy, and if that energy was not enough, right, you could not eject the electron. And so that's where we came up with this relationship. So energy is equal to, and this is Planck's constant, times our frequency. So don't forget frequency, so that's given in hertz, or 1/seconds. And so here's Planck's constant. So Planck's constant, 6.626 times 10 to the negative 34th. So I might write that somewhere. And then it's joules seconds for its units. And so if you look back at your formula, so you have times frequency, so that's 1/seconds. So joule seconds times 1/seconds leaves you with just joules for energy. And so again, here's our other formula. So I would write these down somewhere, top of your homework paper or your periodic table. So our energy is equal to Planck's constant times the speed of light over the wavelength. And so we can say the energy of the photon of light is directly proportional to the frequency. So that makes sense, right? We saw that high frequency means high energy, and then inversely proportional to wavelength. So of course we saw all those things, right? Our radio waves, those long wavelengths are low energy. And so now we're at 1923. And so now de Broglie is examining the wave behavior of electrons. And so de Broglie proposed that particles could have wave-like behavior. So basically, he's saying that everyone has a wave-like behavior, including us. It's just that our wavelength is so small compared to how large we are that it doesn't matter. But he was saying that because electrons are so small that their wave character then would be significant. So we'll do some calculations. And so he predicted then that the wavelength of a particle was inversely proportional to its momentum. So given by this relationship, so the de Broglie wavelength is equal to Planck's constant divided by, and that's mass times speed for momentum. And so in this formula, I should tell you, so mass needs to be in kilogram for momentum, and then that means this is again speed, so meters per second. And so now let's compare what he was saying. So let's first find the de Broglie wavelength of an electron, and then we'll compare that to an average human. And so first we need the mass of an electron. Anybody have that by any chance? So 9.109 times 10 to the negative 31 kilograms. And then the average velocity of an electron is 5.62 times 10 to the 6 meters per second. And so we're given everything we need. So this is, of course, a constant. So Planck's constant, 6.626 times 10 to the negative 34 joules second. So everything's in our appropriate units. So again, kilograms, meters per second, joules second. So now we just have to plug everything in. So plugging it into our formula, 6.626 times 10 to the negative 34 divided by, and don't forget your parentheses, so my mass times my speed, so divided by my momentum. And so now we get wavelength. And so let's just walk through the units of that. So remember we plugged in, so that's joules seconds. And then, I got screwed. No, that's right, joules seconds, so divided by mass, so divided by kilograms, divided by speed. And so now this gives us, so divided by seconds, so joules times second squared over kilogram meter. And then joules is also equal to kilogram meters squared. Oops, let me do that in a different step. So is equal to kilogram meters squared second squared. So now we have over kilogram meters. So now, over, I lost a second squared somewhere. Oh, because joules is kilogram meter squared over second squared. So now that's where my other second squared came in. So that cancels, kilograms cancels, leaving you with meters. So that was a long way to get to our units. And so that was how many sig figs? Looks like we were limited to 3. So 1.29 times 10 to the negative 10 meters. And so that's on the atomic level, right? We said that angstroms was negative 10. So that's pretty significant if you're the size of an electron. And so now let's look at what your de Broglie wavelength would be. Anyone know what a person weighs in kilograms roughly? It's about 60-ish kilograms. And let's just say they're moving at about 1.5 meters per second. And so now we'll just do the same thing. So plug it in, do a wavelength is equal to Planck's constant divided by mass divided by speed. And so let's plug that in. 6.626 times 10 to the negative 34. Divided by my momentum. And so what do we get for our de Broglie wavelength? So do we get this value when we plugged it in? Thumbs up, thumbs down? Oh, thumbs down? It's always possible I punched something in wrong, too, so. Do other people get this, not get this?
I got 1.26 to negative 6.
Check your parentheses. I'm staring at mine, making sure I didn't do anything. Thumbs up, thumbs down. So I see at least one confirmation, 2 confirmation. All right, and so what do we see about this number? So 7, I probably should have given myself more sig figs, but oh well. I guess it doesn't matter too much. So 7 times 10 to the negative 36 meters. And, I mean, how small is this compared to us, right? So that is pretty tiny. So that's why our de Broglie wavelength does not matter. All right, any questions on that chapter? So we're just going to move to practice problems because that's a lot of this chapter is math. And so let's try this one. A laser with a wavelength of 554 nanometers gives a total energy of 1.25 times 10 to the negative 2 joules. So how many photons then? So take a couple of minutes, How might you approach this? What do you know? Where can you get energy from? I'm watching the chat too. So how can we get the energy of one photon, or what do we know?
It's probably wrong, but we take the equals hc divided by wavelength and mess with it to make it e times wavelength over h equals c, and it's all from there.
Yeah, that looks good. Although, right, you can just plug it into here, right, to find energy? Is that what you said? So let's do that, because this is just the energy of one photon. So that's just saying how much each packet carries at that wavelength. And so we'll just plug everything into here. So of course we have to convert this to meters. And then that gives us energy of one photon. And then we can just divide by the total to get how many photons. So let's do that. So let's first convert, so 554 nanometers to meters. And I keep punching everything in wrong today. There we go. So 5.54 times 10 to the negative 7 meters. And so that H and C are just constants, so I'll just write them out. Oh, and that's 10 to the 8th, so 3 times 10 to the 8th meters per second. And so what do you get when you plug it into your calculator?
No, so can I ask why you use 10 to the 9th instead of 10 to the negative 9th to do your conversion? Isn't it 10 to the negative 9th nanometers to 1 meter?
So it's 10 to the 9th nanometers are in 1 meter.
Really, thank you.
No, it's all, yeah, it's always confusing with the conversion factors. That's why I only use positive ones. But, yeah, so maybe for the exam, like you want to write out your conversion factors, you know, in whatever form's easiest for you, all positive. And then, so I got this.
Yeah, I did too.
I got at least one confirmation. See some more nods. All right, excellent. So energy, whoops. My page leaps away. So 3.59 with rounding times 10 to the negative 19 joules. Again, that's one little photon. And so let's see how many total photons were in that laser. So now we know, just have to divide 1.25 times 10 to the negative 2 divided by my answer. And so I get a lot of photons. Let me know if you get that. So 3.48 times 10 to the 16 photons. And so I'll just write out what I did. So just take the total and divide. Let's try your homework out. So let's do just number 1. I can always run up and get homeworks. I think I left them in my office. So I'll write out number 1 and then I can grab some more copies. But it just says calculate the wavelength and energy of a photon of light with a frequency of 1.0 times 10 to the 14 hertz. And then it also asks what region is this in? So what region of the electromagnetic spectrum? All right, so let me see if I can find more homework copies while you work on it. homework copy. Anybody else? Oh, sorry. Oh, sorry. Anybody else in this? So did we get an answer for this one already? So walk me through. So what do we need to plug in to calculate wavelength?
The speed of light divided by the velocity.
Frequency. So excellent. And so speed of light is just a constant divided by our frequency. And so what do we get when we do that?
3.0 times 10 to the negative 6.
So get that as well. So 3.0 times 10 to the negative 6. So good job with those two sig figs and meters. And so energy, so how do we get energy? So Planck's constant times frequency. So 6.626 times 10 to the negative 34 times my frequency again. That gives us something in joules. Oh. So probably on the order of, actually you don't need a calculator, so you can just add, right? So this is just times 1. So just add negative 34 plus 14. So what does that give you?
6.6 times 10 to the negative 20.
So 6.6 times 10 to the negative 20 joules. Yeah.
Would it be wrong to use the Planck's constant times the speed of light and divide by the wavelength?
No, you could do that. So you plugged in energy equals hc over wavelength. So you had found the wavelength and then plug this in. Yeah, that's perfectly fine. And that's what's kind of nice about this chapter. I mean, I know there's a lot of formulas everywhere, but then they all kind of circle around so you can double check yourself.
Hertz is equal to 1 over seconds, right?
Yes.
So for the other, so for the 3.0 times 10 to the negative 6, could that have been meters over seconds? No.
Sorry, I'm just not following. So on this
So,
part,
yeah, so on the bottom we had,
so this is 1 over second, and this is,
oh, so it would be meter seconds.
yeah, so this is meters seconds. So divided by 1 over seconds, but then that 1 over seconds flips to give you seconds. So then it gives you meters. Yeah, units.
They're tripping me up for sure, thanks.
Now they're super useful in physics, I swear. At least I thought they were because I didn't understand the physics, but at least you could like unit match. Any other questions on this problem? Oh, and then it asks, so what region? So now we need to find my electromagnetic spectrum, if I could find where it was. And so we could either judge by the frequency, so they give us a frequency, we calculated the wavelength. So let's try to find it by wavelength. So 10 to the negative 6 roughly, a region, or 1 to the 14 hertz. So where do you think this lies about? So infrared. question?
I'm just curious, what's the difference between the formula E equals H times V and E equals HC over the wave?
So they're just the same, right? So you can derive them. Because you have E equals HC over wavelength, but then C divided by wavelength is equal to frequency. Yeah, so everything's just plugging around and around, so we just plug either this for this or vice versa. And so it's all about just whatever form you're comfortable with, whatever information you have, and again, it doesn't matter. You can solve for this and then plug it in. It all works out. Let's see. Sorry, I'm glancing around your homework on which one I want to do. So let's do on like the second page, number 7, where it says calculate energy and wavelength of a photon emitted when it goes from the 7 to the 4 energy state in hydrogen. So do we calculate energy, or how do we want to approach it? Which formula do we like? So we could do this a few different ways. So what did Joel set up first?
Could we use the equation E of n equals 2.1, negative 2.18 times 10 to the negative 18 times 1 over 7 squared minus 1 over 4 squared?
Except I think we want to do,
The other way around?
yes. Although it shouldn't matter with your answer too much, just give you, like I said, the wrong sign. this was our initial, so it's final minus the initial, but that looks good. And again, you could have done a different approach, but all the answers, all the final answers will be the same. So 1/4 squared, oh, if I could plug things in right. Minus 1/7 squared times my energy. So do we get this for the energy? And so I'll just put it positive. So energy, so 9.18 times 10 to the negative 20 joules. And so why the sign thing is kind of weird, so it's formally negative, so you're thinking about energy being released. But again, so you're just thinking of that difference, so that's kind of why it's a negative. And then if you're putting energy in, then you're kind of promoting the electron then. And so you could also think of this released. So you could formally, again, put a negative sign on there. But I'm not looking too much at the sign convention of that, just kind of know what you'll see. And then, so once we have our energy, what could we do? Or we could also take a different approach too, not use the energy. Someone tell me what you did next.
I took the E equals HC divided by wavelength, and then moved it so its wavelength is equal to E times
Or HC over E.
yes.
And so then let's do that. And again, you could have done something else. So you could have also used that other formula, 1 over the wavelength, to get you there. But let's just plug this in first. And so you can tell where you wouldn't want to plug in a negative energy here, because that just wouldn't make sense. So. And so now I know when I do this, though, it should really be positive. So my wavelength is equal to 2.16 times 10 to the negative 6 meters. And so again, I'll just kind of write out the alternate approach. Or you could have started with calculating this and then found the energy with the formula. So alternatively, maybe you like this form of the formula. So 4 squared minus 7 squared. And so I'll just plug this in to show you. So multiply it by our constant, and then take the inverse. And so that gives us, right, the same answer we just got from the other method. So 2.16, maybe a slight discrepancy with rounding, but as long as you're showing your work, I'm not going to penalize for any rounding. So about 2.16, 2.17 times 10 to the negative 6 meters. And then, of course, again, you could plug this back into here now to get energy if you started with this. You can double check yourself. So they all go round and round. So let's try. Were there other ones from the homework that look tricky? And we'll try one not from the homework.
We did number 9.
Number 9. So the first time, because there's only one number 9, right? The de Broglie wavelength one, is that the one? Let's do another page. So calculate the de Broglie wavelength for an electron traveling at 2.0 times 10 to the 5th meters per second. So I'll give everyone some time to try it. See, do we plug it in? So if we look back, so our formula, if we remember for de Broglie wavelength, was just Planck's constant divided by the momentum. And then if we remember from earlier, the mass of the electron was 9.109 times 10 to the negative 31 kilograms. And so now we can plug everything in. And so what do we get when we plug it in? So is this what people got when we plugged it in? Thumbs up, thumbs down. I see a thumbs up in the front, thank you. Other thumbs up, sweet, all right. So it looks good. And so they didn't specify units, so we could leave it in these units. So 3.64 times 10 to the negative 9 meters, or convert it, so just multiply it to give you 3.64 nanometers as well. Any questions on that one?
What was the 9.109? That was the weight of.
Yeah, so it's just the mass of the electron, and then it has to be in kilograms to match up with all the units. And just make sure you're multiplying these first before you divide. Oh, I see thumbs up in the chat too. Excellent. Let's do another one. And so how would you solve it if you just see a problem where it asks calculate the escape energy of an electron from a hydrogen atom? So what are we thinking for escape energy? How could we calculate that? What formulas do we have? So how do we calculate energy? So you said we had that formula. So this was just one method. Oops, sorry. But then what other formulas do we have for energy? So this is correct, but this doesn't really help us right now. Yeah, so that still doesn't help us, but what other relationship do we have with energy?
You can't set that to zero, equal to zero, energy equals zero.
No, because we're trying to solve for that, but I kind of hinted at it on lecture on Tuesday, so I don't know if people remember. See if I can find the right graph in my notes. So remember when I was talking about these energy levels, right? And they just kind of keep going and going and going. But then eventually if you get to n equals infinity, that's going to be considered your electron popping off and flying away. And so anytime you see this escape energy, it's kind of a fancy signal for you to use. So we have, right, that energy equals negative 2.18. Now I already forgot what factor. Times 10 to the 19th, right? Somebody help me out. Too many formulas on this one. Oh. Negative 10? So what's the... That's what happens when you have too many formulas. I would hope if I could find it, but... There it was. So yeah, you were right, negative 18. So we have this. And so now we can plug in. So we'll have final minus initial. So escape energy, final is going to be infinity. And so 1 over initial, just assuming 1, so 1 squared. And so now we can just multiply. So of course 1 over infinity just becomes zero. So 0 plus, or excuse me, minus 1. So now we just have negative 1 times our energy. So then our escape energy is 2.18 times 10 to the negative 18 joules. And then how do we feel about just the number 5, the first ionization energy one? So maybe let's just go over that. So basically, which has the larger first ionization energy? And it gave you some pairs. And so let's look at the first one. So potassium versus sodium. So who has the larger first ionization energy? So sodium. And then next pair, so neon versus fluorine. What'd you guys say? So neon, right? Because it has a full octet. And they're right next to each other. And then sodium versus neon. So neon again. So there's neon, and then sodium's actually on the next period, so that's of course going to be lower in energy. Neon, and then the last one, nitrogen versus oxygen. So this might have been a weird one. trying to find our ionization energy pattern. Yeah, so you remember this oddity? So if you looked at it here, so ionization energy, so neon, fluorine, and then oxygen, nitrogen. So remember that was kind of weird? And so we had to explain that nitrogen actually had the larger first ionization energy. Since if we compared nitrogen has one in each P, so it was not very happy to lose one of those, compared to oxygen. So again, you have to pay a price to pair the electrons. So then if you kick one off, right, the energy you had to pay is given back, and so that's a little bit more favorable. That was a tricky one there.
So why is sodium higher than potassium?
So sodium has a higher ionization energy since it's above potassium. So as they go down the periods, right, that electron is held on more loosely. So it takes less energy to kick it off as you go down. Does that make sense? Other questions or anything else from the homework, or any other burning questions or anything else? Or so we're running a little early today, but let's just go ahead and take our 10-minute break, and then let's try to start our quiz at like 11:25 or so. Don't leave. Yeah, take a break, stretch around, get your calculator ready for the quiz. Well, actually, yeah, you might need your calculator. I can get some. Okay, who else? Anyone else need a calculator? So 2, 3, 4 calculators, 5, 6. All right, I will see what I can find. Oh, yeah, yeah.
Ancient.
Well, ancient, if I'm, it's like,
Ready as I would be. What?
so what are we doing? What's it about?
The lectures from last week, I think. Something like that.
It's just the balancing equation.
Yeah. Balancing equations.
I'm naming too, though. Right?
Oh, yeah.
That's when you like mess up naming.
I think I'll be okay.
Usually like specific like iron 3 something.
Anybody else need a calculator?
Except for that's this week. That was
I will stop streaming.